The transformation of manufacturing from localized artisanal craftsmanship to globalized automated mass production stands as one of the most consequential economic and technological developments of the modern era. Prior to the Industrial Revolution, the fabrication of complex goods was fundamentally a bespoke, labor-intensive process, relying heavily on the individual expertise of skilled craftspeople. Individual artisans would meticulously shape, fit, and assemble components by hand, using simple tools, resulting in products that were entirely unique, expensive, and devoid of the consistency required for broad commercial distribution. Early glimpses of sequential production emerged as early as the 12th century at the Venetian arsenal, where laborers produced ships by moving them down a canal, fitting new components at each designated stop to achieve a remarkable output of one completed ship per day. However, the true conceptual foundation for modern manufacturing was laid with the advent of interchangeable parts. In the late 18th century, French gunsmith Honoré Leblanc championed the use of standardized firearm components, though his ideas faced resistance from fellow artisans protecting their custom trades. Concurrently, English naval engineer Samuel Bentham applied uniform parts to the production of wooden ship pulleys, but it was Eli Whitney who successfully popularized the concept in the United States, utilizing standardized equipment and unskilled labor to manufacture firearms at scale. These historical precedents coalesced at the dawn of the 20th century to revolutionize the automotive industry. In the early 1900s, automobile chassis were typically placed on stationary blocks, and workers carried materials to the cars to assemble them one at a time, making vehicle ownership a privilege strictly reserved for the wealthy. In 1901, Ransom E. Olds patented the first automotive assembly line for his curved dash Oldsmobile, enabling his factory to turn out an unprecedented 20 units per day and increasing overall output by 500% within a single year. Building upon Olds' methods, Henry Ford introduced the moving assembly line at the Ford Motor Company's Highland Park plant in 1913, utilizing heavy steel rails and motorized conveyor belts to tow the vehicle chassis from station to station. By strictly dividing labor into discrete, repeatable tasks and enforcing a sequential organization of tools and personnel, Ford achieved a staggering increase in efficiency, reducing the assembly time of a single Model T from over 12 hours to a mere 93 minutes. This innovation democratized the automobile, slashing prices and fueling the massive economic prosperity of the 1920s. However, the extraordinary productivity gains of the early 20th century assembly line exacted a severe and unsustainable human toll. The implementation of scientific management principles effectively stripped the deep, multifaceted knowledge of the skilled artisan from the factory floor, replacing refined mental and manual skills with simple, monotonous tasks repeated endlessly. The comprehensive understanding of the manufacturing process was transferred from the workman's cap to the manager's brains, relegating the human operator to a mere biological extension of the machinery. Workers were tethered to the relentless machine-driven pace of the line, performing isolated operations such as securing a specific bolt or applying a single weld hundreds of times per shift. This environment fostered extreme boredom and psychological degradation, requiring only minutes of training before a novice was expected to automatize their movements to keep pace with the mechanized belt. The physical demands were equally brutal. The assembly line itself became an unyielding machine boss, operating at terrifying speeds that forced workers to push their physiological limits continuously. Factory managers frequently employed speed-up tactics, arbitrarily accelerating the conveyors alongside stretch-out strategies that doubled up machine assignments to ensure workers were never idle. The resulting work environment was characterized by unbearable line speeds and severe occupational hazards, where laborers operating milling machines, lathes, and punch presses frequently risked catastrophic injury and amputations. This punishing regime heavily favored the physical resilience of youth, By the time workers reached their late 30s or early 40s, many were physically burnt out and unceremoniously discarded onto the industrial scrap heap by personnel managers who refused to hire older individuals. Despite the famously high wages offered by Ford's $5 plan, the extreme physical exhaustion, the profound psychological monotony, and the rampant exploitation of immigrant labor rendered the human element the most vulnerable and volatile link in the manufacturing chain, frequently leading to a drop in quality, output, and widespread worker dissatisfaction. Simultaneously, the automated machinery that populated these early factories, while incredibly fast, suffered from severe mechanical rigidity. The pinnacle of early automation was the cam-driven automatic lathe, a technology originating from designs pioneered by Swiss engineer Jakob Schweitzer in 1872 and heavily utilized throughout the 1920s and beyond. These machines relied entirely on fixed physical geometry to govern motion, utilizing a central rotating camshaft. As this main shaft turned, specially profiled metal cams mechanically pushed and pulled an array of levers, linkages, and up to 6 simultaneous tool slides. The precise physical shape of the cam dictated the exact moment a cutting tool would feed into a bar of raw metal, how deeply it would cut, and when it would retract to allow the part to be parted off. This pure mechanical automation was capable of extraordinary speed and consistency, operating continuously for 24 hours a day and completing machining cycles in mere seconds without any manual intervention during the cycle. Because the motion trajectory was mandated by solid steel rather than vulnerable electronic signals, these machines were immune to network interference, servo response fluctuations, or software glitches, guaranteeing exceptional dimensional consistency with tolerances around plus or minus 0.02 of a millimeter for the mass production of uniform items like screws, pins, and standardized fasteners. Yet this mechanical genius was fundamentally inflexible, representing a massive bottleneck in the face of evolving consumer demands. The geometry of the machine was entirely hard-coded into its physical components. If an engineering design changed, or if the factory needed to produce a differently sized component, the entire machine had to be halted. Technicians were required to physically remove the heavy steel cams and machine entirely new ones with different mathematical profiles, an expensive and time-consuming retooling process. The automated lines of the 20th century were magnificent instruments of rigid mass production, highly effective for producing millions of identical parts, but they were entirely incapable of mass customization or rapid adaptation. As global consumer demand began to fracture into thousands of different preferences, requiring factories to switch rapidly between different car models, varying electronics, and customized appliances, the hard-coded mechanics of cams, gears, and synchronized drive shafts became an unsustainable limitation. A disruptive shift was desperately required to decouple physical motion from fixed hardware, paving the way for the era of programmable digital flexibility and the rise of the articulated robotic arm. The liberation of the industrial assembly line from the tyranny of fixed mechanics began with the conceptualization of the programmable transfer machine, marking the dawn of the robotics age. The very first known iteration of an industrial robot dates back to 1937, when Griffith Bill P. Taylor constructed a crane-like device utilizing mechano parts, powered by a single electric motor and capable of automating the stacking of wooden blocks through pre-programmed patterns. However, the true commercial genesis of the industry occurred in 1954, when George Devol, widely recognized as the father of robotics, filed the first industrial robot patent. Partnering with Joseph F. Engelberger in 1956, Devol formed Unimation, the world's first company dedicated to producing industrial robots. In 1962, Unimation initiated the robotic automation of the automotive industry by installing the Unimate robot at a General Motors die-casting plant in New Jersey. These early iterations were primarily utilized for material handling and spot welding, transferring objects within a limited radius of 12 feet. While effective at removing human workers from hazardous, high-temperature environments, these early iterations lacked the fluid dexterity required for complex assembly tasks. The architectural revolution in manufacturing kinematics arrived definitively in 1969 with the invention of the Stanford arm by Victor Scheinman at Stanford University. As the first all-electric, six-axis articulated robotic arm, the Stanford arm introduced an unprecedented level of dexterity and spatial control, expanding the role of robotics far beyond simple material transfer into the complex realms of intricate assembly and continuous path arc welding. Scheinman continued his pioneering work at the Massachusetts Institute of Technology, developing the Silver Arm in 1974, which utilized touch and pressure sensors for feedback control via a mini-computer. He subsequently founded VicCarm to manufacture these designs, eventually selling the technology to Unimation, leading to the collaborative development with General Motors of the Puma robot in 1978, which became a ubiquitous fixture in modern assembly line production. The absolute mastery of the modern industrial robot lies in its mechanical architecture, which is specifically designed to replicate and vastly exceed the biomechanics of the human arm. This superlative dexterity is achieved through 6 distinct degrees of freedom, allowing the machine to navigate 3 linear dimensions, x, y, and z, and 3 rotational orientations, roll, pitch, and yaw. The physical structure begins at the robust robot base, which houses the main power conduits, the main control unit, and securely anchors the massive machine to the factory floor. The first axis operates at this base, providing a sweeping side-to-side rotational movement. This joint powers a rotation range that frequently spans greater than 180 degrees from the center point, defining the breadth of the robot's primary work envelope and allowing it to access components situated completely behind its core body. Above this foundation, the second axis acts as the primary shoulder joint, powering the heavy forward and backward extension of the entire lower arm linkage. The third axis functions as the elbow, raising and lowering the upper arm to dictate the vertical reach of the machine. In highly articulated models, this joint permits the arm to reach back over itself, drastically expanding the accessible geometric workspace. The true finesse of the 6-axis architect, however, is localized in the complex wrist mechanism, which comprises the final 3 degrees of freedom. The fourth axis rolls the upper arm in a continuous circular motion, reorienting held parts from horizontal planes to vertical alignments, commonly referred to as the wrist roll. The fifth axis dictates the pitch and yaw, functioning much like a human wrist tilting up and down or swinging side to side on a mechanical hinge. Finally, the sixth axis rotates the end effector, the specialized tooling attached to the robot, such as a welding torch, pneumatic gripper, or suction array, in a twisting motion that frequently exceeds a full 360 degrees in either a clockwise or counterclockwise direction, a physical feat entirely impossible for human anatomy. This compounding series of joints enables the robot to snake into the confined, structurally complex chassis of an automobile to execute a spot weld in a geometrically restricted space, or to approach a delicate electronics casing from an acute angle without disturbing adjacent microscopic components. Powering these sophisticated sequences of articulation are high-torque servo motors, which serve as the indispensable muscular system of the robotic architecture. Unlike standard induction motors that run continuously at a constant velocity, a servo motor is a highly specialized actuator designed explicitly for exact positional control, velocity regulation, and rapid, powerful acceleration. The internal anatomy of a servo motor consists of a direct current or alternating current electric motor, a complex gear train, a precision feedback sensor, and a dedicated control circuit. The motor generates the raw rotational motion, while the integrated gear train reduces the motor's high-speed output to vastly increase the torque, enabling the robotic arm to manipulate heavy payloads without sacrificing delicate accuracy. To achieve the near-zero backlash required for micrometer precision, modern servo motors frequently utilize advanced strain wave gear technology, which minimizes efficiency losses and ensures that when the motor halts, the massive kinetic energy of the robotic limb ceases instantly with zero mechanical slop or vibration. The fundamental distinction and primary advantage of the servo mechanism is its integration into a highly responsive closed-loop feedback system. Embedded directly within each of the 6 joints is a high-resolution optical or magnetic encoder, or a precision position potentiometer, that continuously measures the absolute rotational position, speed, and trajectory of the motor shaft. This sensor relays high-frequency telemetry back to the robot's central controller, which constantly compares the actual physical position of the robot limb against the mathematically desired coordinate programmed into the software. If a spatial discrepancy of even a fraction of a degree is detected, the control circuit instantaneously modulates the pulse width modulation signal, injecting precise bursts of electrical current to adjust the motor's motion and correct the trajectory in real time. This continuous microsecond-level cycle of measurement, comparison, and correction is what grants the 6-axis robot its fluid, superhuman precision. In complex manufacturing tasks, such as continuous path robotic arc welding, the robotic arm must maintain the welding torch at an exact, unwavering distance and angle relative to the curvature of the metal, moving at a strictly regulated velocity to ensure the molten weld pool forms evenly without burning through the base material. High-torque servo motors provide the immense rotational force necessary to maneuver heavy steel armatures, while simultaneously demonstrating the microscopic delicacy required to halt that massive kinetic energy at a specific sub-millimeter coordinate. Crucially, the selection of these motors requires meticulous inertia matching, ensuring the inertia ratio between the motor and the load falls within an optimal 3-to-1 or 5-to-1 margin, allowing the servo to respond instantly, maintain fluid motion profiles, and avoid unnecessary mechanical stress on the couplings. Ultimately, this awe-inspiring physical architecture is entirely subservient to the invisible software governing every single millimeter of travel. The transition from cams to code means that the robot's motion profile is no longer a physical artifact carved in steel, but a highly adaptable digital string of waypoints, arrays, and kinematics calculations. Engineers utilize intuitive teach pendants to manually guide the end effector through a desired sequence, recording the precise angular coordinates of the joints at each step to build an operational program. Alternatively, offline programming software allows manufacturing engineers to generate complex multi-axis toolpaths directly from 3-dimensional computer-aided design models, translating virtual geometry into actionable servo commands without ever halting the physical production line. This seamless, instantaneous bridge between digital intent and physical execution is what fundamentally separates modern robotic assembly from its rigid mechanical ancestors, transforming the modern factory floor from a static arrangement of iron into a dynamic, infinitely reprogrammable engine of creation. While high-torque servo motors and articulated steel structures form the muscle and bone of the modern assembly line, the Programmable Logic Controller operates as the indispensable central nervous system, orchestrating the chaos of the factory floor into perfect operational harmony. Introduced to the industrial landscape in the late 1960s to replace massive, convoluted, and highly fault-prone cabinets of hardwired electromechanical relays, the Programmable Logic Controller is a ruggedized, industrial-grade computer designed specifically to withstand the severe vibrations, extreme temperature fluctuations, pervasive dust, and intense electromagnetic noise inherent to heavy manufacturing environments. In its modern incarnation, the controller possesses processing capabilities that rival high-end commercial computers, yet it operates on a fundamentally different computational paradigm that prioritizes absolute determinism, long life cycles, and unwavering real-time reliability. The core operational mechanism of the Programmable Logic Controller is the scan cycle, a continuous, rapid-fire loop that serves as the unrelenting heartbeat of the automated factory. In the initial phase of this cycle, known as the input scan, the central processing unit reads the digital and analog states of thousands of input devices scattered across the assembly line, simultaneously interrogating proximity sensors, optical scanners, limit switches, thermal probes, and safety interlocks. In the subsequent phase, the processor executes a user-defined logic program, often written in specialized visual programming languages such as ladder logic, function block diagrams, or structured text, evaluating the fresh input data against a complex architecture of conditional statements, logical contacts, and relay coils. This logic incorporates specific timing elements, such as timer on-delay functions that delay an output after an input is triggered, timer off-delay functions that keep an output active after a signal drops, and counters that track event repetitions. Finally, in the output scan phase, the controller updates its output modules, firing precisely timed signals to open pneumatic valves, engage heavy motor contactors, or trigger the robotic arms to initiate their pre-programmed kinematic sequences. The controller concludes with internal housekeeping, managing diagnostics and heavy communication loads. This entire cycle from perception to cognition to physical action occurs in a matter of milliseconds, and in high-performance applications within mere microseconds. This relentless computational speed and unblinking vigilance effectively eliminate human error from the synchronization of the assembly line. A human operator may succumb to physical fatigue, momentary distraction, or sensory overload, leading to misaligned parts, skipped fastening steps, or disastrous safety breaches. The automated controller, conversely, applies its programmed logic identically across millions of continuous iterations. It ensures that a robotic welding sequence will not initiate unless a sensor explicitly confirms that the automotive chassis is clamped to the exact required tolerance and that the previous robotic cell has completely retracted its arms. If a critical anomaly is detected, such as a sudden spike in motor torque indicating a jammed component, or a broken infrared light curtain signifying unauthorized human intrusion, the controller reacts instantaneously, halting the massive machinery orders of magnitude faster than human reflexes could manage, thereby preventing catastrophic equipment failure, ensuring uncompromising quality control, and safeguarding human life. The supreme strategic advantage of this computational architecture, however, is its capacity to orchestrate mixed-model assembly lines, representing a definitive disruptive break from the static inflexibility of the historical Fordist era. In a traditional factory, an entire production line must be halted and extensively retooled to switch from producing one vehicle model to another, costing days or weeks of lost productivity and immense capital expenditure. Modern automotive manufacturers, exemplified by the radical production optimizations pioneered by companies like Tesla, have leveraged the power of programmable logic controllers deeply integrated with radio frequency identification technology and centralized manufacturing execution systems to achieve instant dynamic switching between entirely disparate products. In these highly advanced environments, the physical component itself dictates the bespoke assembly process it will undergo. As a bare vehicle chassis, a motor casting, or a sensitive battery module travels down the automated conveyor, it is affixed with a passive RFID tag containing a unique encoded hexadecimal string identifier conforming to electronic product code standards. As the unit approaches a specific robotic cell, an industrial antenna, such as a Zebra RFID reader connected via localized edge computing, interrogates the tag. decoding the hex string into plain text and bouncing the unique identifier back to the local programmable controller. The controller instantly cross-references this precise data with the overarching manufacturing execution system, the supreme air traffic controller of the entire facility, which manages production orders, tracks quality defects, and conducts statistical process control using robust Oracle and SQL Server databases. Based on this split-second digital handshake and real-time database query, the controller transmits a specific command to the waiting 6-axis robot, instructing it to seamlessly transition from the complex welding program optimized for a compact sedan roofline to the entirely altered geometric parameters required for a heavy sport utility vehicle. The robot automatically swaps its end effector tooling using automated tool changers, adjusts its spatial boundaries, and executes the newly assigned sequence without the main assembly line ever pausing its forward motion. This network-driven algorithmic agility ensures that production bottlenecks are virtually eliminated, allowing the factory to instantly respond to fluid market demands and automatically dispatch the correct parts via warehouse replenishment systems without any manual intervention. This deep integration of operational technology with information technology is further supercharged by Tesla's unboxed process, which utilizes massive presses for gigacasting to mold entire vehicle underbodies in a single piece, eliminating hundreds of individual components and welds, and allowing the factory to build cars in separate modules before a final assembly stage, potentially reducing factory footprints by 40%. Furthermore, the intelligence of the modern factory extends far beyond the physical hardware through the pervasive deployment of digital twins and advanced simulation technologies. Utilizing sophisticated software platforms like Siemens Process Simulate, Plant Simulation, and NX, automation engineers create exhaustive, high-fidelity virtual replicas of the robotic cells and the entire production line, long before any physical metal is bolted to the factory floor. This process of virtual commissioning allows engineers to meticulously test and optimize the robotic kinematics in a risk-free digital environment, ensuring that the heavy steel arms can reach every required spatial coordinate efficiently without hyperextending their joints, colliding with safety fencing, or creating cycle time bottlenecks. As industrial automation surges toward the late 2020s, these digital twins have rapidly evolved from static design validation tools into continuous living performance optimization engines. By synchronizing in real time with the massive telemetry streaming directly from the physical robots, including localized vibration frequencies, motor torque loads, temperatures, and high-resolution encoder feedback, the digital twin utilizes embedded artificial intelligence and machine learning algorithms to constantly monitor the health and efficiency of the machinery. If a digital twin's pattern recognition model detects an anomalous vibration pattern or a slight misalignment in a robotic arm's second axis, it can predict an impending mechanical failure or a degradation in weld quality weeks before it physically manifests. This allows maintenance to be scheduled proactively during planned downtime, saving millions in avoided defective batches and catastrophic mid-production breakdowns. Through this continuous closed feedback loop of sensor data capture, real-time cloud synchronization, and AI-driven predictive analysis, the digital brain of the factory ensures that the physical muscle operates at the absolute zenith of operational efficiency, frequently boosting cycle times by 5 to 15%. The synthesis of highly articulated robotics, high-torque servo actuation, and intelligent high-speed control architectures manifests most visibly in the sheer velocity and perfectly synchronized choreography of the modern production floor. Nowhere is this breathtaking speed more apparent in the deployment of specialized automation like high-speed Delta robots, utilized in continuous pick-and-place applications. Suspended above fast-moving conveyor belts, these lightweight, multi-armed machines leverage the complex geometric principles of parallel kinematics to achieve blistering operational speeds. Governed by advanced trajectory planning algorithms and aided by integrated 2D and 3D machine vision systems, a Delta robot can identify, target, grasp, transport, and precisely place varying components at phenomenal rates exceeding 200 full motions per minute. To the human observer, the end effector is a literal blur, manipulating delicate electronics, sorting packaged goods, or arranging pharmaceutical vials at a velocity that far outstrips the limits of human visual tracking and manual dexterity. When integrated with advanced linear transfer systems, such as hybrid cam systems utilizing stop-and-go manufacturing processes that allow for temporary pauses up to 32 stations, this relentless throughput maximizes operational density, allowing factories to output massive volumes of inspected, assembled, and packaged product within drastically reduced physical footprints. As industrial automation pushes aggressively toward the technological realities of 2026, the integration of advanced telecommunications infrastructure is fundamentally redefining how these rapid physical processes are coordinated and optimized. The widespread deployment of private 5G networks and the foundational elements of emerging 6G systems introduces the critical capability of ultra-reliable, low-latency communication to the factory floor. Traditional wireless networks, heavily hampered by bandwidth constraints, packet loss, and significant signal latency, were entirely insufficient for controlling heavy, fast-moving machinery, where a communication delay of just a few milliseconds could result in a catastrophic physical collision. The 5G standard, however, provides a seamless, highly deterministic flow of vast quantities of data, enabling instantaneous gigabit-speed communication not just between a robot and a centralized server, but directly peer-to-peer between the robots themselves. This ultra-low-latency networking is the vital, non-negotiable prerequisite for the deployment of industrial robot swarms, decentralized autonomous mobile robots, automated guided vehicles, and collaborative robotic arms operating in tight, highly dynamic proximity. Unlike traditional industrial robots that are rigidly bolted to the floor and strictly sequestered within protective steel cages, modern swarm robotics relies on continuous spatial negotiation to maintain efficiency and safety in environments designed for humans. Surpassing early bio-inspired algorithms like basic particle swarm optimization, these modern fleets are powered by advanced multi-agent reinforcement learning algorithms, including multi-agent deep deterministic policy gradients and Q-mix-based mixing networks. Operating on lightweight onboard AI deployments and distributed software bus networking like Harmony OS, these swarms continuously calculate and broadcast their positional vectors, sensor data, and intended trajectories over the 5G network. By utilizing fuzzy logic inference systems and decentralized actor-critic neural networks, the individual robots dynamically adjust their speeds and routing to avoid collisions, navigate around unexpected obstacles, and maintain optimal formation without waiting for explicit instructions from a centralized server. In an advanced automotive or logistics facility, this translates to dozens of autonomous platforms weaving seamlessly through a maze of articulated robotic arms, delivering specific components to the exact coordinates required by the assembly sequence. Simulated and real-world experiments demonstrate that these algorithms result in smooth, collision-free movement with an astonishingly low average deviation of less than half a meter from moving formation targets, maintaining perfect swarm harmony through continuous, microsecond-level digital communication. Ultimately, the supreme advantage of this synchronized high-speed automation is realized in the massive, quantifiable leap in dimensional consistency and quality control that has become the strict, uncompromising standard for modern manufacturing. In the realm of industrial arc and spot welding, human capability is fundamentally limited by inescapable physiological realities, Muscle tremors, visual fatigue, the intense heat and toxic fumes of the environment, and the inevitable decay of concentration over an 8-hour shift dictate that manual welds inherently suffer from dimensional variance. A highly skilled human welder, even when operating under optimal conditions, might maintain a tolerance window of plus or minus 1 to 2 millimeters, making them 5 to 10 times less exact than their automated counterparts. However, an automated robotic welding system, completely insulated from fatigue and guided by rigid servo mechanics and closed-loop feedback, routinely lays down complex weld seams with a variance of merely plus or minus 1/10 of a millimeter, with specialized arc welding setups holding tolerances as tight as half a millimeter or better. Furthermore, the integration of advanced computer vision and artificial intelligence for real-time defect tracking, utilizing advanced models like YOLO4 and MASE, robotic systems can identify weld problems with a staggering 97.35% accuracy, achieving weld depth errors as minuscule as negative 0.06 millimeters. This absolute repeatability is non-negotiable in the production of modern electric vehicles, where massive integrated structural components must align flawlessly to ensure the integrity of the vehicle's structural battery pack and aerodynamic profile. If the heavy robotic arms joining these complex gigacastings deviate by more than a fraction of a millimeter, the entire modular assembly process fails entirely. This relentless demand for microscopic precision is even more pronounced in the consumer electronics sector. The complex assembly of modern smartphones, wearables, and medical devices requires the manipulation of fragile ribbon cables, the meshing of microscopic gears, and the insertion of densely packed logic boards within aluminum housings, where the available dimensional clearance is frequently measured in micrometers. Traditional manual metrology methods, relying on manually operated hand tools like calipers, height gauges, and micrometers, are vastly insufficient for the scale, complexity, and speed required, prone to false readings based on slight alignment errors, thermal expansion from body heat, and human inconsistency. Following the engineering principle of the 10-to-1 rule, which mandates that measurement tools must be 10 times more exact than the part's tolerance, the assembly of micrometer tolerance components necessitates robotic intervention. To achieve this requisite accuracy, modern factories deploy parallel continuum robots and advanced coordinate measuring machines, integrated with automated optical inspection systems and 3D laser scanners. Driven by high-resolution optical encoders and sophisticated Coursera rod-based kinematic models, these highly specialized robotic systems routinely achieve mind-boggling positioning accuracies of 3.3 micrometers and orientational precision of 0.5 milliradians, pushing the absolute physical limits of automated positioning. Operating well beneath the threshold of human perception, these advanced manufacturing robots execute delicate pin insertions, apply conductive adhesives, thread microscopic nuts, and fasten micro screws with an exactitude that ensures every single device off the line meets impenetrable standards of water resistance and internal durability. When an inline automated metrology system detects a dimensional variance in a supplied component, the software communicates directly with the robotic arm in real time, instantaneously adjusting the insertion trajectory to compensate for the deviation, completely avoiding the production of scrap and ensuring that production never halts. Through this relentless, accelerating convergence of highly articulated steel, microsecond-level logic processing, pervasive telecommunications, and predictive digital networking, the contemporary factory has entirely transcended its historical origins. The dark, dangerous, and mechanically rigid assembly lines of the early 20th century have been thoroughly dismantled. In their place stands a highly choreographed, exceptionally intelligent ecosystem where digital flexibility drives physical motion, achieving a symphony of speed, autonomous adaptability, and micrometer precision that defines the absolute pinnacle of modern industrial capability.